The last part of our mathematics library is dealing with complex numbers. Now we know a complex number potentially has two parts. It's going to have a real part and an imaginary part. So it means that we can deal with this really simply just using the idea of our array. And it's going to be nothing other than an array with two elements. The first element will be the real part, and the next element will be the imaginary part. So let's say, for instance, in this example here, we wanted to represent the number 2 plus 3i. Then we could generate this as the DC command, so define constant, we'll call it complex, and we'll put it in brackets, and it's 2, 3. And we know that the first value here is the real part, 2, and the second value is the imaginary part, 3i. Now we don't actually put the letter I in here. We've got no need to do that. We simply need to understand that the second part here is always the imaginary part. So in this instance here, what we're going to do is we're going to return the real part of this number. So we're going to pass the complex number 2 plus 3i, or we're going to push it onto the stack. So we push complex onto the stack, and we're going to push the address where we're going to put the real part, and then we're going to jump to the subroutine which generates the real part of the complex number. And all we're going to do in effect is just return the value 2. So this 2 plus 3i goes into the subroutine and we return the value of 2. And 2 goes into this address, real underscore address. And you can see that's the answer here. So that's actually relatively straightforward. Now if we want to generate the imaginary part, instead of returning the value of 2, we want to return the value of 3. So in effect the answer here becomes 3i. But we don't actually again have the I anywhere in this. The I is just understood because we know we're dealing with complex numbers. Now if we want to perform complex addition, then we can put the complex number A. In this instance I've generated 2 plus 3i, and the complex number B, 3 plus 5i. And I've given a position in order to save the answer to, and that's complex underscore C. So we're going to push each of these onto the stack, and then we're going to jump into the subroutine that does the addition. Now in order to add complex numbers together, we just add the respective components. So the real part gets added to the real part, and the imaginary part gets added to the imaginary part. It is no different than, say, adding vectors together. We add them per component. So the answer to this will be 2 plus 3 is 5, and 3 plus 5 is 8. So we'll have a 5 and an 8. But in effect that represents 5 plus 8i. And again we can go through the same process for subtraction. And I'm not going to talk through this because it's exactly the same as the addition one. The only difference is we perform the subtraction component wise. Now if we want to generate the complex conjugate, if we had a number, for example 2 plus 3i, then the conjugate is 2 minus 3i. What we do is we negate the imaginary part. And that's what this does here. So we're going to push the complex number, we're going to push the address where the result is going to go, jump to the subroutine, and it's going to negate the complex part, and it will return 2 minus 3. So again, straightforward. Now we can do a multiplication by a scalar. So in this instance here we have the scalar 2 plus, we have the complex number 2 plus 3i, and we have the scalar, in this instance it's a value of 2. And then we have the position where we're going to save the result. So we pass the complex number A, we pass the value for the scalar. Now in this instance here, the way I've done it, it looks like I've passed in the actual address for the scalar, and then it'll, within the subroutine, it'll go from that address and it'll find the actual value, and it will actually generate the correct answer. Okay, and now the position where it's held is in complex B, so we pass that in as well, and we go through the multiplication, and whenever you multiply it, you simply multiply 2 times 2 and 2 times 3, so the final answer will be 4 plus 6i. Okay, so I'll have 4 in one memory location and 6 in the other memory location. Now the final one is a little bit more complicated. We're going to multiply together two complex numbers. So again, I've picked 2 plus 3i, 3 plus 4i. So when we multiply these together, we're going to multiply the 2 times 3 and then 2 times 4i. And then we're going to multiply the 3i with the 3 and then the 3i with the 4i. And we've got 4 components here. So the 2 times 3 is going to give us the value of 6. The 2 times 4i will give us 8i. 3 times 3i will give us 9i. 9i plus 8i is 17i. And then the final one is going to be 3 times 4 is 12. And I times I is I squared. So I squared is minus 1. So that'll be minus 12. So the final solution for that is going to be the 6 minus 12, which is minus 6 plus 17i. So they're relatively straightforward, and it's a nice little exercise in generating a complex arithmetic within our machine. So let's pick one of these and we will see it actually working. And the best one to pick, I suppose, is the most complex one, which would be the multiplication. So let's work through this one now. I've loaded the code into the machine, so let's simulate it now. And that's it running through. I'll pull up the actual values here as a reminder. So we are expecting to get the answer minus 6 plus 17i. So it shouldn't take too long for it to run through to get that answer. And that's it, finished now. So let's stop this and we'll jump in and we'll have a look and see where it's held the answer. So at 8500 we have the original complex numbers, 2 plus 3i, 3 plus 4i, and this is the final answer. It's minus 6, so that is the value for minus 6, FFFA, and the value for our 17 in hex is 0011. So that's us done a multiplication of a complex numbers. So that's all for this video, and that's the last of the mathematics library. Now we can continue to expand on the mathematics library, and I've just got a basic setup with some basic subroutines as ideas for moving forward with, so we can continually add to this if we want to. The next thing we'll look at is a string library. So thank you for listening. I'll get you on the next video. Goodbye.